Hi everyone, my name is Aryan and today I want to talk to you about functional programming. So I work at OKGrow where we help companies build JavaScript apps. We also do consulting, app development, and training. So functional programming. Functional programming is a programming paradigm. So today I'm going to talk about a few different paradigms that are listed here. But before we get into that, the word paradigm basically, or mindset, or even language means a way of thinking about software. And basically, there are defining principles that dictate that paradigm. So today I'm going to talk about mostly functional programming, which is usually a subset of declarative paradigm, and also object-oriented programming, which is a subset of the imperative paradigm, with more focus on functional programming. And then at the end, I'm going to show some examples of where you can use this today in your JavaScript code. So I'm sure each person here has a different story of how they got into programming and computer science. So I'm going to take you through my personal journey, which started with imperative languages and object-oriented programming. So my first introduction to programming was back in grade 6, where back in Iran, they taught us flowcharts and Pascal. And then later, Delphi, which is a Windows version of Pascal. Has anyone here used Pascal? So like 5 or 6 people. So these are both imperative languages. Then I went to high school where I learned about C++. So all of these are still imperative languages, which means each line explains what the program should be doing at each moment in time. Or each statement here changes the program's state. So what is state? In this example, state is the content of all of these variables at any point in time. So languages like this, oops. So languages like this tend to change the state or mutate the state, which means they change variables. They change the content of variables, which is something that languages like C++ love doing, but declarative languages or functional languages hate doing that. So a concept that is tied with imperative languages is object-oriented programming. This is the idea that everything is in objects and classes. So this models our real world really well. That's why the examples are usually things like animals or cars. So in this example, you can have an animal class, and you have a cat and a dog class, which inherit from that animal class. So if you call a function that is called make sound on the animal class, depending on whether it's a cat or a dog, it will bark or meow. So after learning object-oriented programming, I had a pretty solid mindset of how to write code. This was until I went to University of Waterloo for computer science, where they wanted to prove to everyone that they don't know how to write code. So they taught us this. So this is Scheme. Scheme is a functional and declarative language, which means it hates changing state. It hates changing the content of variables. So this was a bit hard to learn at first because it's so different from anything else that I knew how to write. So the reason for this big difference between functional programming and object-oriented languages is that they come from different parents. They come from different mindsets. So as you can see, object-oriented programming is a mindset of imperative paradigm, and functional programming is a subset of the declarative paradigm. But something that is important to remember here is that these are not mutually exclusive. So if you're writing functional code, doesn't mean that you're not writing the other kind anymore. Especially with JavaScript. JavaScript is a multi-paradigm language, which means it supports both types and even more paradigms. So even in one file, you may end up using this mindset or the other one, depending on your need. But what does imperative and declarative really mean? So imperative languages focus on how the program should execute and get to its goal. So this is very close to how the CPU works or how the computer works underneath. Whereas declarative languages care more about what the program does. Now let's take a look at a simple example. So let's say we want to calculate the Fibonacci series and display it on our website for some reason. This is a series where each number is calculated by adding the last two. Now let's take a look at the code for them. This is the declarative approach, and that's the imperative approach. So you can see that the declarative approach is much closer to how I explained the app to you, and it's much easier to read. It's also closer to its mathematical representation. Now you have to understand that this is not just a difference in syntax or how you write it. It's also, it gets the same result, but it works in a very different way. Your program underneath works in a very different way. In the imperative approach, you have these 5 variables. No matter how big the number is, if you want to calculate Fibonacci of 1,000 or 5, you still have these 5 variables, and they keep changing. The value of them keeps changing until you get to the result that you want. This is in contrast with the functional approach, where instead of having only 5 variables, you have a lot of function calls. So if you want to calculate Fibonacci of 6, you say that get Fibonacci of 5 and 4, and then those two each call a bunch of other functions. So you don't have a lot of variables, but you have a lot of function calls, which means if you want to calculate Fibonacci of 1,000, it takes more space in your memory in your laptop than if you were going to do the same thing the imperative way. Now let's try running both of these in the terminal. So on the, is this big enough?
Bigger.
Bigger. Oops. All right, so on the left side, I have the imperative approach, and on the right side, I have the declarative approach. Now you can see that the declarative approach is much prettier. Now I'm going to try to calculate Fibonacci of a number using both methods. I'm going to try number 42 for both. Oh, sorry, I think yeah, that's correct. So you can see that the declarative approach takes a little bit more time than this one. Now, if I try this for a larger number, like 45, it's probably never going to finish before the end of this talk, but the imperative approach, you can get the answer for 1,000 right away. And this one is still going. So you can see that the declarative approach is way slower, but it's much easier to read. However, more than a demonstration of performance of these two, I just wanted to point out how they work differently under the hood. This is just something to keep in mind when you're writing code to see if readability and maintainability is more important to you or performance. In most cases, in most everyday cases, the answer is readability, because you're working with a group of people and you want to be able to maintain this app in the future. And probably the number of calls that you're going to make is not going to be thousands, and it's going to have a minimal effect on the performance. But this is just something to keep in mind when you're writing code. So getting into functional programming can be, or the mindset of it can be challenging at first, because there's a lot of new words and terminology to learn. So I'm going to just take you through the core principles and try to explain it as easy as I can. So the 3 main principles of functional programming are pure functions, immutability, and currying. So I'm just going to briefly go through each of these, but you could probably give a talk about each item, because so I suggest looking them up and researching them. So the first one is pure functions. Pure functions basically don't depend on anything outside of their scope. So if you're grabbing data from outside of the function, or you're changing stuff from outside of the function, which is also known as side effects, if you're doing those things, you're not doing pure functions. So here's an example of an impure function. This is not pure because we're using this variable 1 inside of this function. So to make this pure, we just move that inside. Here's another example of an impure function. This is impure because on line 4, we're changing the content of the value that is our input. So afterwards, the value that we pass to this function is going to have a new value, which is not what we want, in this case at least. This is also known as side effects, which is changing stuff. Like you run your function, and it has a side effect, which means it's changing something that is not inside of this function scope. So we defined pure functions, but why should you care, and what are the benefits of them? So it turns out that pure functions add a lot of value to your program. The first one is idempotent. So I have to be honest, I had to look up the pronunciation of this word, which led me to this YouTube comment, which always makes me remember it. Basically, every time that you run an idempotent function, you get the same result. So they're safe to rerun as many times as you want. So idempotent functions are safe to rerun, which is great for testing. And also it's great for reasoning about your application, because otherwise you would have to keep track of a state of your application. But with idempotent functions, you know that all the information is inside of the function. This is also good for testing. Because for the same reason, because you don't have to keep remembering what the state of your application is. And lastly, it's great for memoization which means you can cache the result of your function. So if you have a function that you have to call 1,000 times, but there's no point, like the value is not changing, you can memorize the value or cache the value and only use that value once. So going back to our Fibonacci example, I'm going to show the same code but using memoization. So all I've added is this word here, which means if you already calculated Fibonacci of 5, don't do it again when you're calculating Fibonacci of 6, because you need that number. So it just stores it somewhere. So with this method, I don't have that performance issue anymore. Oops, sorry. So I can calculate, hopefully, is that 1,000? Yep. Yeah. So the central point of functional programming was never changing state, which leads us to immutability, which basically means never changing state, which in JavaScript translates to not changing objects or arrays after defining them. So never giving an object a new value, which is a pretty common practice in today's JavaScript. So in our impure example, we were mutating input. If we had immutable types, we would get an error on this line because we're not allowed to change the value of person. Here's an example of a code that mutates data. We have person, and we try to poorly copy it and then give the new person an age. But we accidentally change the value, the age of the first person as well. So you can fix this issue using ES6 object assign, which basically copies the initial object rather than copying the reference. So this will make it immutable because we're not changing that anymore. Easier, you can just use the spread operator, which does the exact same thing here. So you've probably already used immutability. If you've ever used map or filter, those are immutable functions because they don't change the input array or object. Most strings functions are also immutable because they don't change the string that the function is running on. I know there are some exceptions, but I don't know the reason for them. So one benefit of immutability is that you can run a bunch of code in parallel, and you won't have any problems because you know that if you didn't do this, two things would try to access the same variable, or two things would try to write to the same place. But with immutability, you know that that's never going to happen. So if you think this is a useful idea, check out these two libraries. The first one, Immutable by Facebook, and Ramda, which give you a lot of tools to do everything immutable. And then finally, carrying. So this is a kind of an odd concept to grasp at first, so I'll try to give a very simple example. Let's say you have a function that takes 10 parameters as input. Carrying is the idea that instead of that one function, you have 10 functions that each take one variable or take one parameter. So why is this a good thing? Because it allows for all those little functions to be rearranged and reused all over your app. So you get this small library of all these little functions that are really easy to read and easy to use. Also, if you don't have all 10 parameters at once, you can only pass it like 2 parameters. So if you do that, instead of getting the result back, you get a function back that is waiting for the remaining 8 parameters. Now we're going to look at some examples of that. So this is a code without carrying. How do I know that? Because it's taking 2 parameters. It's taking x and value. And then later on, this is a modulo function, which I've tried to make an is-odd function from it by just returning the value of modulo 2. So here's the same example, but with carrying. So how do I know that? Because each function on line 1 is taking only 1 parameter. And then I can make an is-odd function much easier than the previous method. And this gets more beneficial when you have more complicated and more input values. So in general, carrying makes code more readable, and yeah, it gives you the library of little functions to use all around your app. So one of the main benefits of carrying is that it allows for function composition. So if you remember from math, if you had these 3 functions, you could wrap them in each other, so to create a new function. Or you could use this little circles, which basically mean the same thing. So f o g o h means f of g of h of x. So the same thing applies in JavaScript. You probably already know you can do that. But instead of that, you can use the compose function, which gives you back another function that is a composition of all those 3. And then you can apply that on your input value. So one thing to remember about compose is that it's read right to left. So similar to the math format, this first calculates h of x and then g of x. And I mean, h of x passes the value to g and then passes that value to f. So carrying and compose are 2 concepts that work really well together. If you have functions that only take 1 parameter, you can compose them on top of each other. But if they take more than 1 parameter, you have to carry them before composing them. So compose, in this example, this is not a built-in JavaScript function, but you can get it from a lot of different functional programming libraries like Ramda, Lodash, or Recompose, which these libraries also give you a lot of other tools to play with for functional programming. So we've been talking about passing functions and returning them, which leads us to the last concept that we're going to talk about today, which is higher order functions. So a higher order function is a function that either takes a function as an input or returns a function. So our Fibonacci example, the declarative one, was a higher order function because it returns a function. Also, our modulo function was a higher order function. You've probably already used higher order functions if you've used JavaScript. If you've ever used the event listener, that's a higher order function because it takes a function as an input. if you've ever used map or filter, these are also higher order functions because they take a function as an input. So in React, this idea of higher order functions kind of translates to higher order components, which are not the exact same thing, but they're kind of similar idea. A higher order component is a function that takes a component and enhances it and gives you back a new component. So higher order components are great for cross-cutting concerns, which is when you want to use the same piece of code across different components. So this is a very common use of higher order components where we're taking GraphQL queries and mutations, and we're taking all these functions and composing them to our component, which means our component will have the benefit of all these functions, and we can use them across different components. If we didn't have compose, we could still do the same thing, but then it would look very ugly. You would have to wrap each of these functions inside of each other, and it would be a lot harder to read, write, or maintain in the future. So these were just some cool examples of cool things that you can do with functional programming. I hope at least you learned something that you didn't know about before, and I hope that this inspires you to go and look up functional programming and try to use it in your JavaScript code today. That's it.